So how exactly does the wave spread out? Well, if the wave is traveling at the same speed in all directions, then we would expect the energy to spread out in a sphere, like this diagram indicates. So at a distance from d from the source, then it will be spread over a sphere with radius d. We can see that if we're observing at this distance from the source, then no matter which direction that distance is in, we'll always be receiving the same amount of energy, because the wave is spreading out in all directions at the same speed. So this means we can figure out the amount of energy passing through each unit of area. The total energy is going to stay the same, so we can put that as a constant on the numerator, but it will be divided among the entire area of the sphere. The surface area of a sphere is 4 pi r squared, so if we want to divide the total energy by the area, we end up with this figure here. Total energy over 4 pi d squared. And this will tell us the amount of energy divided by the amount of area, or in other words, the amount of energy per unit area that comes out through the sphere. So this is a measure of how intense a wave is. Which of the following is an example of a 3D wave? We have a few options here. Starlight from the night sky, a compression wave in a spring, ripples in a pool of water, and a signal in an electrical current. Now, remember that we talk about a wave being 3 dimensions if it spreads out in 3 dimensions. That means that it has to be able to travel both forward and back, left and right, up and down. So let's start from the bottom. We can say that a signal in an electrical circuit sometimes behaves like a wave, but is it 3-dimensional? No. In an electrical circuit, we move back and forth along the wire. We can only spread out in one direction, that is, forward or back along the wire, so it's a 1-dimensional wave. How about C, ripples in a pond of water? In this case, we're spreading out a bit more than the electrical signal, except we're only spreading out in 2 dimensions. The dimensions are forward, back, and left and right. We're not spreading out in the up and down direction, because we have to spread out along the surface of the water. So this means that C is not right either. How about B, a compression wave in a spring? A spring is a 3-dimensional object. Well, it is, but the wave can't spread out in 3 dimensions. In a spring, the wave can only travel along the length of the spring, that is, forward or backwards along the spring. It doesn't spread out in any direction. So the answer is not B. Our final answer is A, starlight from the night sky. Now at first this might seem a little dodgy because we know that light travels from the star to the Earth, and if it's 3-dimensional, then it must be spreading out. So surely the stars would be very dim and not visible. But it turns out that close to the stars are so bright that even at a distance of millions and millions of kilometers, we can still see the light from the star. So the other thing is that, of course, we're able to see starlight no matter where we are around the star. Our sun, for example, is a star, and no matter what time of year it is, we can still see it, assuming it's the daytime. So A is the correct answer. Starlight is a form of electromagnetic light, so it must spread out in all directions.